Hello, my name is Steve Miller. I'm a math professor at Williams College, and I want to talk to you today about Pascal's triangle, in particular Pascal's triangle modulo 2. So this is a slight revision of a short little recording I gave about 6 years ago, where I fixed up some of the code to make things display a little bit nicer. I'd like to thank my student Kevin Keith from the University of Michigan, who helped with a lot of the coding. So first, a couple of preliminaries. So n factorial is the number of ways to order n objects with order matters. Factorial is n times n minus 1 all the way down to times 1. And we said 0 factorial equal to 1 is essentially one way to do nothing, also known as n. Then n choose k is the number of ways to choose k objects from n when order matters. It's n factorial over k factorial n minus k factorial. You can see this by the n factorial divided by n minus k factorial is just going to give you the number of ways to choose k objects from n when order matters. And then when we divide by k factorial, that takes away the order. And the last thing that I want to remark on is the binomial theorem. If we expand x plus y to the n, we get the sum of k goes from 0 to n choose k, x to the k, y to the n minus k. So this appears in Pascal's triangle. And so here's Pascal's triangle. So you have two diagonals of 1, and then every element is the sum of the element above to the left plus above to the right. So zooming in on this section here, 4 would be 1 plus 3, 6 would be 3 plus 3, and so on and so on. So here 15 is 10 plus 1. And of course we have the ones over here, so this element here, if you want, you can view it as a 0, 0. Now this beautiful identity, n plus 1 choose k, is n choose k plus n choose k minus 1. How could we prove this? Well, one way to prove this is by just brute force algebra. You could just write out what things are, clear the denominators, and we would be done. But it's not really an enlightening proof, so I want to give a story proof. So let's assume we have n Red Sox fans and 1 Yankee fan, so we have n plus 1 people total, and we want to know how many ways can we choose a group of k people. Well, one way is we have n plus 1, and we want to have k people. By definition, that's just n plus 1 choose k. Another way to view it is, well, we may be fortunate and not have the Yankee fan with us. There's 1 choose 0 way not to choose the Yankee fan, and then we choose k fans of the Red Sox. Or we do choose the Yankee fan, there's 1 choose 1 way of doing that, and now we need to get up to k people total, so we have to choose k minus 1 of the Red Sox fans. And so because we're counting the same object 2 different ways, they must be the same. And this is a general principle of combinatorics. You can do something 2 different ways. You can often use that to perform the algebra you need in a nice way and prove some identities. Notice that the tops always add up to n plus 1, and the bottoms always add up to k. So let's draw a few more rows. So you have 1, 2, 3, 4. What you notice is that this is the 0th row. The 4th row is just going to be the coefficients you get from the binomial thing when you expand out x plus y to the 4th. And now we're going to look at Pascal's triangle in a new way. So what we're going to do now is we'll put a dot if n choose k is odd, and we'll leave it blank if it's even. So if we just have the first row or the 0th row, it would just be a dot. If we do the first 4 rows, it looks like this. And we can keep going further and further and further and asking, what is it going to look like? And so if we do the first 8 rows, we start to see a little pattern emerging. So this little part over here is repeated down here and down here. And the question might be, what would we see if we continue? So the version I posted about 6 years ago looked at some code that I wrote, and we had the images coming from the left and moving to the right, and we always sized things up so it always filled the same box. We just added more and more rows. And normally, since we have Pascal's triangle coming down like this, after 6 years, decided, well, why not just rotate it, have to draw a plot. And so that's what we're going to do now. So again, I've written some mathematical code to do this. If anybody's interested, just email sjm1@williams.edu and happy to share the code. And so what we're going to do is we're going to alter so that the triangle stays in this region over here. And as we add more and more rows, we're going to just keep shrinking. Unfortunately, we do not have the budget for infinite screen. And so what we'll do now is we will run it and see what happens as we add more and more rows. And so you can start to see the pattern emerging. And you can see this incredible self-similarity. There's a beautiful fractal structure here. This is the Sierpinski triangle. It has a non-integral dimension. There's a lot of wonderful results. And so if you've never seen this before, it's just a nice, fun little application to see. It's also an interesting question as to what is the most efficient way to generate this. So if you know one row, how would you generate the next row? Would you use recurrence relations? Would you use the self-similarity? Would you use the fact that you only need to work with things even and odd? So I'll leave that as questions for you to think about. So as remarked, so that this is similar to the Sierpinski triangle. So the way the Sierpinski triangle works is you take an equilateral triangle, and at each stage you remove, after splitting into 4 equal parts, the center, the middle of the 4 new triangles. So you keep 3/4. If you continue this, you'll see that eventually you have 0 area. You will have at least the outside of the triangle. So this is an object whose dimension should be somewhere between 1 and 2. And a nice definition of dimension is if you dilate your figure by a factor of r, if you get c copies, then r to the d equals c. So if we start off with a line and we triple it, we now have 3 copies of the line, so the dimension would be 1. If we have a square and we triple both the length and the width, we now have 9 copies, so the dimension would be 2, and so on. When you do the calculation here, if we double, this part over here will expand out to become the whole triangle. So we get 3 copies. So in r to the d equals c, r would be 2, c would be 3, and we get that the dimension would be somewhere between 1 and 2, about 1.58. So there's a lot of wonderful stuff you can see here. We just did Pascal's triangle by looking at the remainders modulo 2. What other questions could you ask? Well, there's not surprisingly a lot of different links and things that you can see. And I will just show a little bit. Here's what you would see if you look at things modulo 3. You can do modulo 4. And of course, you can do lots of different moduli. And this is looking at the remainders when you divide by 2, by 3, by 5, by 4, whatever. You could ask, do you see differences if you divide by primes or powers of primes versus composite numbers? Which numbers have similar patterns? So there's a lot of wonderful questions to ask, and I encourage you to explore. Have a great day.